Yeah, let's do it. Okay, so proven angle relationships. This is going to be super similar to the last video in some ways, although there are other types of things going on here. So the big idea is we're really just doing the same proofs as the last section, except instead of segment addition postulate, we're using angle addition postulate. That's a big part. Okay, so part of angle plus part of angle equals big angle. But also we start really proving some useful things here. Okay, so the biggest one is vertical angles are congruent. Okay, that's the biggest idea. So whenever any two lines intersect, you get these angles opposite from one another that are congruent, and you get another pair over here that are congruent. This is always true. We're going to use this in tons of proofs throughout the year. This is one of the most repeated theorems we will use, like reflexive property of congruence and this vertical angle theorem. Two of the most common, just come up all the time, right? Two other useful things are linear pairs sum to 180. So that'll show up different books, like IXL, different places will word it differently. But the big idea is if you have a line and you have two angles, whatever this one is, this is, so let's call this x, then the other one is 180 minus x, because these two angles add up to a straight angle, or 180 degrees. So the linear pair or supplementary, linear pair sum to 180. However your book defines it, a linear pair adds up to 180 degrees. Okay, and then the other one, all right angles are congruent. That is just a statement we will use rather than reproving it over and over. So if we come across two 90-degree angles or two right angles, we just say they're congruent because all right angles are congruent. Okay, so we have the same two postulates to start here as the last one, except instead of saying you can measure a line segment, it's saying you can measure an angle. You set 0 on one side of the angle, and then you measure a positive number of degrees, and you get a number, right? Between 180, because we're still defining angles as less than 180 degrees, because otherwise, anytime an angle would be formed, it would be two angles formed, and then it gets like, which one are you talking about? And then you have to describe minor or major, and to avoid that ambiguity, we say we're only dealing with angles less than 180, and then we can easily expand it later. Okay, so you can measure an angle from 0 to positive. Again, we're not going to use this as a step in a proof that often, but it's a fundamental assumption we all agree on, right? It's one of those postulates that we say, this is so obvious, we can quantify this, right? We can make up any units we want. We chose degrees, 360 slices to cut a circle into, and then we just count how many of those slices are angles, right? And we use decimals or fractions, that's okay. All right, angle addition postulate simply says a piece plus another piece adds up to an entire angle here, right? So the measure of PQR, the top little portion, and the measure of RQS, the rest of the big angle, adds up to the measure of the entire angle, right? So piece plus piece equals whole of an angle, okay? Got it. All right, so now we've got our first two theorems here. Okay, so one, I'm just going to give you the proof. The other one, I'll prove. They're very similar. But a theorem, remember, is something that we prove and then we reuse. And what it does is it makes future proofs shorter and more elegant. I also come from a computer science background, and it's the idea of functions, right? Rather than writing everything in one place, you package something up that you're going to reuse, and you put it off to the side with a name, right? And then whenever you need to use it, rather than putting those 10 lines of code or the 10 steps of proof, you just put the name there. And you go, oh, we're going to call on this function, or in this, we're going to call on this theorem. And what it does is it says, there's 10 steps, and you can refer back to it at the beginning of the book or somewhere. I have those steps written, but I don't want to write all 10 here. I just want to write one, okay? So for 2.3, it's just saying if two angles are form a linear pair, then they're supplementary. Another way to say this is a linear pair sum to 180, right? So I didn't like this proof so much, so I just pasted it here. The other one, though, we will go ahead and do, okay? So you can refer to this later. So complements here. If the non-common sides of two adjacent angles forms a right angle, then the angles are complementary angles. So in other words, given this picture, and the fact that this is a right angle, right? So given ABC is a right angle, then prove that the measure of angle 1 plus the measure of angle 2 equals 90 degrees. Okay, so we start with the given, right? So 1, angle ABC is right angle, right? That was one given. Okay, well, what is, like anytime we have a word, the very next step is, what is the meaning of that word? How do we turn that into a mathematical expression we can use? Well, the definition of a right angle is the measure of this angle is equal to 90 degrees. That's the definition of right angle. Okay, and now we need to say, well, what are we talking about here? We really want to say that the measure of angle 1 and the measure of angle 2, that's what we want to get here, right? That's what we're aiming for. So let's do that. How do we say that the measure of angle 1 plus the measure of angle 2? That's the angle addition postulate. Remember, so the piece of an angle plus the whole angle equals the total. So let's go down here. Now, we can't directly use the 90. That's not something we can do. We're just using angle names. Okay, so the measure of angle 1 plus the measure of angle 2. So those two angles added together equal the big angle. So measure of angle ABC. That's what we know from the angle addition postulate, right? Piece plus piece equals whole. But we know that the measure of angle ABC is 90, so we can just swap that out, right? So now we have the measure of angle 1 plus the measure of angle 2 equals 90 degrees, and that's by substitution property of equality. Or actually it could be transitive because 90 is equal to this, and this is equal to this, so they're equal to each other. So either one, I'm going to say substitution this time, prop of equality, but transitive property would totally work there too. And let's double check that's exactly what we wanted to prove for the given. So now we can go ahead and use that. If we ever come across right angles, we can say the two angles sum up to 90 degrees. Oh, sorry, I am sorry. It is saying then the angles are complementary. That is the end of our proof, not that they sum to 90 degrees. Let's add one more step here. Then angle 1 and angle 2 are complementary. And step 5 is, that's the very definition, right? If they sum to 90 degrees, then that means that the two angles are complementary. So that's the definition of complementary angles. Okay, so that was a little proof, right? A little 5-step proof using angles. Very analogous to what we did using segments, right? The segment addition postulate. But now we have more angles we can use, right? We have complementary, supplementary, linear pair, vertical angles, adjacent angles. So there's a lot more we can do rather than just with segments, okay? So here we have the same 3 properties of congruence that we're going to have with pretty much every congruence relationship. So reflexive, any angle now is equal to its, or is congruent to itself. Symmetric, again, we're just never going to use that one. Transitive property, if angle 1 is congruent to 2 and angle 3 is the same as angle 2. Well, then that means angle 1 and angle 3 are the same as each other because they're both the same as angle 2. And that's the transitive property of congruence. I put the 3 proofs here. If you want, you can grab the notes and read through these. They're basically just saying it's true in algebra, and then the definition of congruent angles says it's true in congruence. And again, that's the same on all these. You use the property of equality and then definition of congruent angles. Again, you do it on, you do it on the one below. My iPad freaked out there for a second. Still freaking out? Hold on one second. Okay, sorry, I just had to close and open Notability there. It was unhappy. I've been using it for like a week straight without a break. We all need a break. Deep breath, some sleep, reset. So the iPad needed that too. All right, so here's the next 2 theorems. Just basically the same as one another, except one supplementary, one complementary. They're saying if 2 angles are supplementary to the same angle, or it doesn't have to be the literal same angle, it could be just any 2 angles that are congruent, then the angles are congruent to one another. So in other words, if these 2 are supplementary and these 2 are supplementary, then these 2 have to be the same. And that's easy to think about, right? Because if this is x, then this is the supplement, right? So 180 minus x. And then if these 2 are supplementary, we could write this one as 180 minus whatever the other angle is, 180 minus x. And then with some quick algebra, you could just distribute in that negative and you go, this is 180 minus 180 plus x, or in other words, it's just x, right? So we could just use algebra to prove this, and the same thing down below, but this is going to be one that we reuse a lot, okay? So I put the proof of complementary right here. just so you can see how the book did it in a 2-column format. And then I'm going to go ahead and prove 2.6, the supplementary one, because we're going to do that pretty often, okay? So I set it up here. We have angle 1 is supplementary angle 2. Angle 3 is supplementary angle 2. We want to prove that angle 1 and 3 are the same. So let's start with the two givens, okay, in this diagram. And then we're going to say, okay, well, if they're supplementary, what do we know? Well, this tells us that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. Okay, and what let us do that? Well, we started with a vocabulary word. So the way we get from vocab to math is always the definition of that word. So definition of supplementary angles. Okay, and then we're going to do the same thing over here. So I'll say measure of angle 3 plus measure of angle 2 equals 180 degrees. Again, that's the definition of the word that we were given, so supplementary angles. Oh, well, look, they're both equal to 180 degrees, so we could just put those together then. And this time, since it's a big expression equal to 180 on both sides, I'm going to use the transitive property, although you could absolutely use substitution here too. So the two angles added up equal 180, which is also equal to measure of angle 3 plus measure of angle 2, because they're both equal to 180. And that was the transitive prop of, and we're in algebra here with an equal sign, so equality. And look, we've got this angle 2 on both sides. So let's just go ahead and subtract that from both sides, and we get the measure of angle 1 equals the measure of angle 3. I almost wrote the wrong angle, right? Just taking away the measure of angle 2 from both sides. So we get, that was by the subtraction property of equality. As we start moving forward and moving more and more into geometry, it's going to be common that the book will just use, or even IXL will just use algebra in general. Right now, as we're still starting, that would collapse our proofs to be like 2 steps. So just to get in the habit of writing 7 or 8 step proofs, we're going to use each separate step of algebra individually just to get in the habit, practicing proofs. It's like when you start working out, you do it with light weights to learn your form, learn breathing. You don't start with the biggest weight and just sloppy, I can do it, rah, and rip muscles and injuries, right? So we're just practicing good habits here. But as we move forward and we're writing longer and longer proofs, we will collapse the algebra down and just call it algebra, right? And that's okay. All right, but that's not where we wanted to end. We wanted to end that the angles were congruent. We want to end back in the world of geometry. So we're going to then go ahead and say, well, if the angle measures are the same, then angle 1's congruent to angle 3, and that's by the definition of congruent angles. Okay, that's what it means for two angles to be congruent. All right, so here's the vertical angle theorem. Oh, this is where we're going to really build our first theorem that we're going to reuse. And we're actually going to use the previous stuff, okay? So just from the image, we know that the two are linear pairs. So I'm going to start from there. And now there's 2 ways you can be given information. You can be given information either in writing, and that's what, often we say we were given their supplementary because literally it was written that these angles are supplementary. But with linear pairs, that's something that you see a picture, or vertical angles too. You see a picture and you go, oh, look, angle 1 and angle 3 are vertical angles. And then you would say the reason is that is given by the diagram, right? You see in the picture that they are. Now, if you wanted to, you could also just say that's the very definition of vertical angles. But then they'd say, well, like, what information did you base using the definition on? And that's why I like saying given by a diagram, because then you're telling them, look up at the diagram, that's where the step came from. But it's really both, right? You're saying I, human, looked at the diagram, and then I, human, know the definition of a vertical angle. So from the diagram, I know that, and then you identify the words, right? So that's what we're doing with linear pair to start. We're saying, oh, okay, well, angle 1 and angle 2 are linear pair. Angle 2 and angle 3 are linear pair. Those are both given in the diagram, okay? And what I want to prove is that vertical angles are congruent. So I'm aiming to prove that angle 1 and angle 3 are congruent. Now, you might see where we're going, right? We just did a very similar proof right here, okay? So if we know angle 1 and angle 2 are a linear pair, and that was given by the diagram, and angle 2 and angle 3 are a linear pair, and that was given by the diagram, then you could go straight to angle 1 and angle 2 are supplementary, and angle 2 and angle 3 are supplementary. Now, every book you're going to use is going to call this something different. So in this book, they call it the Supplementary Theorem. I actually like to just call this, I actually just say the explanation, linear pairs are supplementary. Often if you're using IXL will go straight from there, a linear pair, to measure of angle 1 plus measure of angle 2 equals 180. And their reason will be linear pairs sum to 180. So it really depends on the book, what how you name that foundational step. But the idea is first identify that they're a linear pair, then either go to they add up to 180 or they're supplementary. I'm going to choose going to supplementary because that lends itself well to the proof we just did above. Okay, so those are supplementary. I'm going to say linear pairs are supplementary. Okay, well, if one's supplementary to 2 and 3's supplementary to 2, we just did that here. So we could just use theorem 2.6, which we didn't give a good name to, which is so sad, but we're going to use this theorem that says, well, then we know that angle 1 is congruent to angle 3, and I'm going to restate the theorem. That's often if you just write theorem 2.6, yeah, great. A robot can go look up a lexicon and beep, boop, bop, beep. In chapter 2, there is theorem. That's not helpful for a human to understand. Who wants to go refer to a book? Just clearly communicate. And so I would write, if 2 angles, supplementary to same angle, then congruent. Right? Like, there we go. I justified. Now, yes, you could write theorem 2.6. I don't like writing it that way. So you could, if you wanted, just take this whole proof right here, right? I'm going to zoom out a little bit. I'm going to take this whole proof. Whoops, I missed something. Hold on, let me re-grab this. I'm going to take this whole proof, and I'm going to copy it, and I'm going to say, oh, this theorem right here, you know what that theorem is, right? I'm going to delete it, and I'm just going to paste this whole thing, right? That's what a theorem does. A theorem just says, copy and paste all those same steps. See, linear pairs are supplementary, so then it takes you to 180, takes you to 180. So that's what we're doing when we say, I'm putting a theorem here. So I'm actually going to back up and say, I don't want to put all 1, 2, 3, 4, there's more steps, so there's 5 steps total. Instead of 5 steps, I'm going to just say, boom, 1 theorem, 1 step. We did this theorem, right? And I want to just see last proof, right? That's the idea of a theorem, right? Theorem 2.6, we prove it. Now we can reuse it to make future proofs shorter. That's the idea that we're building on here. Okay, I'm going to pause and jump back to Zoom. We're going to do some more in just a bit. All right, I'm back. So moving forward, here's the other theorems. These all have to do with right angles. They're all pretty short proofs, and I bet you could prove these yourselves. So given perpendicular lines, then they intersect to form 4 right angles, and that's just based off their linear pairs. They're congruent. They sum up to, and so you just end up getting 180 divided by 2 essentially to create all of these. All right angles are congruent. Well, that's easy because they're equal to 90, so they're equal to each other. Definition of congruent angles. So some of these are pretty obvious, but we're stating clearly these short, 2 or 3 step proofs so that we can use these rather than dealing with those details later. So perpendicular lines form congruent adjacent angles. That's really a big part of this right here. If 2 angles are congruent and supplementary, right? So they add up to 180 and they're the same, then they both just 180 divided by 2, then they're 90 degrees, or they're both right angles. And if 2 angles form a linear pair, if 2 congruent angles form a linear pair, again, that's very similar to the last one, except the last one said the general case of supplementary where they're separate. If they're supplementary and the same, then they're both 90 or right angles. This one says if they're a linear pair. So the picture I drew, right? If they're next to each other and congruent, and they form a straight line, 180 divided by 2, right? So I'm not going to prove these in the interest of time. I'm going to jump on to homework questions, but these are all proofs that you can absolutely do, and we could do these in class if you're curious, okay? All right, so let's just start with some homework problems. Find the error. So Thomas looks over here. He's trying to use the angle addition postulate. He says angle ABE, the measure of that, plus the measure of angle EBC adds up to the total of ABC. That seems valid to me, right? He's got the measure of each angle. He's adding equals. Yeah, that's the angle addition postulate. Clear as day, right? The next person says the angle ABE, so that same measure of angle ABE here, plus the measure of angle FBC, this angle here, adds up to the measure of this whole angle. That's not true. We're missing that middle portion in the addition. So no, that is not true, okay? All right, so this one, the error was he should have used angle EBC, otherwise he's missing a piece of the larger angle. Draw 3 congruent angles and use these angles to illustrate the transitive property for angle congruence. Oh, so if we just do like here's angle A, here's angle B, here's angle C, and we're given that these two angles are the same, and we're given, I don't want to, or maybe I'll just draw it in a different color. You don't usually do this, but draw angle marks here and angle marks here. So if we know that angle A is congruent to angle B, and we know that angle B is congruent to angle C, right? Then the transitive property for angle congruence would tell us we can get rid of that middleman, and we can just say, well, then angle A is the same as angle C by the transitive property of congruence. Okay. So let's go to find a measure of each angle numbered. So if measure of angle 1 is 65 degrees here, we already proved that vertical angles are congruent. So we immediately know that this angle right here has a measure of 65 degrees. And these form a linear pair, so we could always subtract, it's not asking this, we could always subtract 180 minus 65, and we get a leftover of 115 degrees on this side, which vertical angle is the same as 115 degrees on this side. So the big idea here is, if two lines intersect, and you know a single angle, let's say this is 10 degrees, then you know every other angle at that intersection. And that is a huge idea, right? 10 degrees there, that means this is 10. That means 180 minus 10, this is 170. That means this is 170. Notice I didn't draw it to scale. I'm not going to draw anything to scale. They're all going to be freehand sketches. The mathematical reasoning will be valid. The numerical calculations will be valid, but I'm not going to use a protractor to accurately draw my sketches. Okay, angle 6 and angle 8 are complementary. So that means this angle plus this angle add up to 90 degrees. And it says measure of angle 8 is 47 degrees. Well, then I can just go, this one is 90 minus 47 degrees, right? Because they add up to 90. Or if you want to do it, you go measure of angle 6 plus measure of angle 8 equals 90 degrees. That's the very definition of complementary. And then I just substitute in the 47. So measure of angle 6 plus 47 equals 90. We subtract 47 and we get the measure of angle 6 is 43 degrees. Okay, over here we got two expressions. We got x minus 4 for angle 11 and 2x minus 5 for angle 12. And what's their mathematical relationship in the picture? Well, those two form a linear pair, so they're supplementary, and so they add up to 180. So I'm going to go ahead and write those two expressions, x minus 4 and 2x minus 5. Those two expressions add up because angle 1 plus angle 12, the measures of those angles adds up to 180. And so then I just combine like terms, so 3x minus 9 equals 180, add the 9 to both sides, and we get 3x equals 189, divide by 3 on both sides, and we get 180 divided by 3 is 69, so we get 63 degrees. Okay, then we just check what it says though. It said find the measure of each numbered angle. So it doesn't care what x is. We need to go back and say, 63 minus 4, that's 59 degrees. And here 63 times 2, that's 126. Minus 5 is 121. And then just to double check, in our picture they should add up to 180. So let's just double check that these add up to 180. Yeah, those add up to 180 degrees. double checked, we're good walking away. Okay, copy and complete the proof of theorem 2.6. Oh, we already did the theorem 2.6 proof, but let's check this out, okay? So we're given that 1 and 2 are supplementary and that 3 and 4 are supplementary. Okay, so that was given to us. And then usually right from there, we have a vocabulary word, so we go ahead and use its meaning. I don't like that this book leaves out degrees, but we go ahead and use that vocabulary's meaning, and what we get is the two things add up to 180 degrees by the definition of supplementary angles. Okay. They also stated this given here, which we haven't used yet. I think better is they should have put that down below when we use it. So I would have personally inserted this down here. But again, we're completing someone else's proof, so it's not to our exact structure, and that's okay, right? Everybody's different and does it in different ways. Okay, so let's go to the next step. Well, how do you think they got to step C? Usually, the place you would look is the step right before. Okay, so they got to step C probably from B. Oh yeah, look, this is equal to 180 and this is equal to 180. So we can just skip the middleman and say they're equal to one another. So 1 plus 2 is the same as 3 plus 4. Got it. That was, I'm going to say it's the transitive property to be more clear, but you could have also said that was substitution. Okay, and then D, now this is why I don't like this, right? So if I'm looking where did D come from, immediately I start looking right before. I'm like, okay, well, did it come from here? And you go, no, and I don't see how it could have come from there. I mean, you'd have to subtract a 2 and a 3, and those are different things, and it doesn't say above, so no, I don't see that, right? And you're like, well, did it come from here? No, I don't see it come from there. Did it come? And you start moving up and up, and if it didn't come from any of the steps before, the only other place it could have come from is the image. And that does happen, right? You pull things in from the image and you would say given from the diagram. However, in this case, it came from step 1. And I think that's just sloppy proof writing. But it came from this angle 1 and angle 4 are congruent. So that was the definition of congruent angles. That is, again, what I would have wrote. Angle 1 is congruent to angle 4 here and put a given as a step after C. Okay, so we got a definition of congruent angles. I'm going to switch back to green. Let's see. Now, how do we know that angle 2 and angle 3 are the same? Okay. Well, they got by combining these two steps, right? Because remember, the subtraction property of equality says we don't need to subtract to the same measure of angle 2 on both sides exactly. We can subtract any two equal values from the two things. And since we know, oh, I'm subtracting the wrong thing. What a goof I am. Okay, I meant you don't have to subtract the measure of angle 1 from both sides. Instead, you can subtract the same or equal measures. And so we know the measure of angle 1 and measure of angle 4 is the same. So we could subtract the measure of angle 1 from the left, and then the same value, but named measure of angle 4 from the right. And since we're subtracting the same value from both sides, we don't break the equality. We don't break the equation. It's still equal. So combining those two steps with the subtraction property of equality, we now get that measure of angle 2 is equal to measure of angle 3. And if the two have equal measures, well, then that means the angles are congruent, and that's by the very definition of congruent segments, okay? All right, this is good. I like that proof. That was nice and clean. Okay, determine whether the following statements are true. And so that's sometimes, always, or never. I love this type of problem. So two angles that are non-adjacent are vertical. Two angles that are non-adjacent. Well, let's try. Well, here's two non-adjacent angles, and they're not vertical. So it's definitely not always for number 8. Okay, well, can we find at least one example? If we can't find any, then it's never. If we can find even one yes and one no, then it's sometimes. Well, let's draw a pair of vertical angles. This angle and this angle are not adjacent. They don't share a side, right? For two angles to be adjacent, they have to share a common side and not be inside one another. So these two angles are adjacent, but these two are not. So two angles that are non-adjacent are vertical. Here's two non-adjacents that are vertical. So there's at least one yes, so it's not never. So this one must be sometimes, okay? Because we came up with one yes and one no of non-adjacent angles. Okay, now let's go to the next one, all right? So I'm going to erase my x's there. So two angles that are congruent are complementary to the same angle. Whoa, that's an interesting wording. So we start with two angles that are congruent. Okay, so we got angle 1 is congruent to angle 2. And we're saying they have to be complementary to the same angle. So we're given, now the wording there is a little funky. So do they have to be complementary? No, right? I could just throw in any random angle. But if they're saying angle 1 is complementary to angle 3, well then yeah, that would for sure mean, right? Well, if it's complementary, right, whatever value, say this was 20 degrees, then that means this had to be 70. And if angle 2 is congruent to angle 1, that means 20 degrees here means this is 20. So then, yeah, 20 degrees for angle 2 would be complementary to angle 3's 70 degrees because they have the same measure. So two angles are complementary to the same angle. I'm going to go ahead and say always, but that's making the assumption you start with one complementary angle and it's asking if then the second one is complementary. But and that's because the way they word two the same, that's a little vague, okay? So I'm going to go with always, but I could see how they could say sometimes, because they could have just said, okay, here's two 20-degree angles. Are they both complementary to the same 50-degree angle? No, neither of them are. So you could see how that could be a confusing question, but I'm going to go with always, because if one of them is complementary to an angle, then yes, it is always true that the other one is complementary. Okay, so let's write a 2-column proof here for this one. Oh, now do we have to write a 2-column, or could we kind of fudge it a little and write a flow chart? I like it. You guys go with flow chart too. Okay, so let's go with Vx bisects. Whoops, let's erase that frame. I should draw the word, write the words first. Angle WVY, okay? And that was given to us. Now, what does that tell us, right? What does bisect tell us? Well, that tells us that it cuts it into, bisect, to cut, it cuts it into two congruent parts. So that tells us that WVY, yep, that tells us that angle WVX is congruent to XVY. Okay, and how did we get from the word bisects to that? Well, that's the very definition of bisects. Okay, and then let's go over to the side and we'll use the other one. Okay, so we know that VY bisects angle XVZ. So looking over at the picture, that's this one, bisects this angle, XVZ. So that is given to us and tells us that the two angles formed, angle XVY, is congruent to angle YVZ. And again, we got from a vocabulary word to some math by using the definition, oh, I should have said of angle bisector, not just the word bisect, because the word bisect means different things for a line segment and there means analogous things, but it's different. It forms two congruent segments or two congruent angles, so it's a little bit different. So definition of an angle bisector. Okay, so now what could we do, right? We want to get that these two are congruent, so let's look at where we've got that. So WVX, well, we got that here. And YVZ, we got that here. Well, they're both the same as XVY, so oh, it looks like we can just bring those two together then and say, well, we know then that WVX must be the same as angle YVZ, and that's by the transitive property of congruence. I told you we're going to use that a lot, right? Okay, good proof, you guys. So now we're just going to do some algebra, and then I'm going to do a couple sometimes always nevers because they're amazing, and then we're going to do one more proof, and that's where we're at. Oh no, two more proofs, and that's where we're at. So it's just examples here. If you want to stop, feel free, or fast forward to the proof if that's what you want to see. Okay, so find the measure of each angle. Well, this one is 67. We can assume this is a straight line because it looks like one, and that's our one semester one allowed assumption. And so we can go ahead and say, well, this is 180, so this is 180 minus 67, or in other words, it's 120 minus 7, 113. Okay, this one over here is 38 degrees. We're looking for this, so if we have the whole 180, right? Well, then that means that the measure of angle 3 plus the measure of angle 4 plus 90 equals 180. And we know that angle 3 is 38, so we got 38 plus measure of angle 4 plus 90 is 180. So all we do is subtract all that stuff from both sides, and we get that the measure of angle 4 is, and 180 minus 90 is 90, minus the 38 leaves us with 52 degrees. Okay, 7 and 8 are complementary, and 5 and 8 are the same. So I'm going to mark that these are the same. It says 7 and 8 are complementary. That means this is a big right angle. That's a giant right angle symbol. And it tells us that this is 29 degrees, okay? Well, if we have a right angle on the left, then the entire 180 minus 90, we always have a right angle on both sides then, okay? So we're just looking for all the values here. So 29 minus, or 90 minus 29, that gives us, this is 61 degrees, okay? That's congruent to angle 8. 5 and 8 are the same, so this is 61 degrees. And on the right, we do 90 minus 61, and we get this is 29 degrees. Okay, so we got mirror image, the same angles on the left and on the right. Okay, so now we've got some variables here. Okay, 15 and 16 are vertical angles. We know vertical angles are always congruent. That's our vertical angle theorem, not the definition. The definition is just identifying what vertical angles are. That's a common mistake people make. So the vertical angle theorem tells us those are the same. So we can go ahead and say x equals 6x minus 290. We add the 290 to both sides to get it over here. We subtract x from both sides to get 5x. And dividing by 5, we get, I think, 58 degrees. Okay, 17 and 18. Oh, it's the exact same problem. Silly. So these are congruent to one another. So we can go ahead and write 2x plus 7 equals x plus 30. Notice how the very first step was geometry, right? We're saying I see vertical angles, so I know they're the same. Boom. Now I've got an equation. The rest of the problem is just algebra. Look up here. It says find the measure of each numbered angle. If I had left number 22 as x equals 58, I'm not getting full credit on that problem. My teacher, ooh, he is cruel. I'm going to turn that in, and my teacher's going to rip my paper in half and fail. Red pen, tear stress. We don't want that. So instead, we're going to go ahead and plug that back in. And we're going to say measure of angle 15 is 58 degrees. And the measure of angle 16 is equal to, we plug the 58 back in, and oh, jeebus, okay, 6 times that, that's 340 degrees, minus 290, so that's 50. Did I mess that? Oh, 6 times, that's 348 degrees, and we minus that, and so we end up getting 58 degrees. Whew, checked out, they were the same. Almost had an error there. Okay. So we set this one up on 23. We subtract the x from both sides. We subtract the 7 from both sides. Again, we don't stop there. We plug them back in. So the measure of angle 17 is 2 23s. That's 46 plus 7. So that's 53 degrees. And the measure of angle 18, because a lot of people would stop there and be like, both are 53. Don't lose the opportunity to double check your work, right? So here's a 23 plus 30, right? I have multiple degrees in mathematics, and I'm checking my work because I want to make sure I didn't make a mistake. Everybody makes mistakes. I make tons of mistakes, just leaving numbers out, skipping steps because I'm in a rush. I'm talking while I'm writing. Take the time to slow down, check your work, okay? Take pride in the work you do, whether it's super easy or difficult. It creates good habits that you'll carry with you into more difficult tasks, and it'll let you cope with difficult situations because you have things to fall back on, structure, routine. It's going to be helpful. Okay, so let's go here. All right, so these two add up to 180. So common mistake is people just go, they are equal, like the last question. I don't need critical thinking. So they add up to 180. So we're going to then write that out. We're going to go 100 plus 20x added to the other angle, 20x. And that adds up to 180 degrees, okay? And then it's just algebra from there, right? So I can't read my own writing. That's kind of embarrassing. Okay, that was a 20, not a 30. So then we add those together. We get 100 plus 40x equals 180. Subtract the 100 from each side. 40x equals 80. Divide by 40. We get x is 2. And then we plug it back in. And so we get the measure of angle 19 is 100 plus 40. or 140 degrees. And we get the measure of angle 20 is 20 times 2 or 40 degrees, sorry. And so just to double check, do those add up to 180? Yes, they do. Woohoo, double check. All right, my favorite type of problem, sometimes, always, never. Okay, let's see, two angles that are complementary. Okay, so they're complementary, form a right angle. Ooh, tricky, classic problem here, right? The loophole here is, yes, of course they can. Here's two complementary angles that do, whoops, I just 30 and 60. Yes, they do, but they could have been 30 and 60 apart. So no, they don't have to form a right angle. Yes, if you add them together, they make 90 degrees. But if they're two separate places, that's not a right angle. Right? A right angle is one angle of 90 degrees. This is two angles that add to 90 degrees. So this is sometimes, okay? So I'm just going to put a big S here for sometimes. And again, it's because they could be separate. And a lot of times on test or quizzes, we'll ask for a counterexample. And so you would be expected to pull that one out. All right, so two angles that are vertical are non-adjacent. Oh, I mean, vertical angles are formed like this. So yeah, two lines intersect. These are the vertical angles which are congruent. They cannot share a side, right? The only way they could share a side if these two sides came together. But if those two sides overlapped, you don't have vertical angles, you have a single line, right? Because the two lines are now the same line, so you don't have vertical angles unless are linear angle. I mean, or straight angles. We haven't talked about straight angles really, but is this straight angle of 100 a vertical angle with a straight angle of 180? What the heck? Blowing minds. No, we are not. No, the way we defined angles is they're less than 180 degrees. So we're gonna say this is always true. However, that is an interesting scenario. Like, is that considered vertical angles? Because the sides of the angle are opposite rays with the sides of the other angle. Oh, it's interesting. Something to think about. I'm going to go with always, but I could see how you might write sometimes. And if you came up to me on a test or quiz and argued that point and used the definition of vertical angles, I would be like, well done. I would high five you and be like, you get those points for sure. Because it's all about logic and clear communication, not rigid old, a book wrote it one way. It's about your creative thought process. Okay, let's go. 29, two angles that form a right angle. So two angles that form a right angle are complementary. So it's saying if there are two angles that form a right angle, are they complementary? Yeah, that's always true. Yeah, because they formed a right angle, so they formed a 90-degree angle. So yes, they're always complementary. Two angles that form a linear pair are congruent. Well, here's a linear pair where they are not congruent. And here's a linear pair where they are congruent. So that's definitely a sometimes. Okay, two angles that are supplementary are congruent. So 10 plus 170, those two angles would be supplementary. And 90 plus 90, those two would be supplementary. But these ones congruent, these ones not congruent. And so definitely that one's a sometimes. So we could have two 90-degree angles add up and be supplementary and complementary. Those would be two right angles. Or we could have any two angles that add up to 180. So yeah, that's definitely a sometimes. Two angles that form a linear pair are supplementary. So a linear pair means they actually make a line together, right? So that one, if they're already a linear pair, then they have to add up. So that's always. If they had asked the question in reverse, that would be just like number 27. If it was supplementary, you can't assume that they're next to each other. But if they're a linear pair, they have to be supplementary. Yes, they make a straight line of 180 degrees, but the converse of that would not be an always. The converse would be a sometimes. Okay, so let's go ahead and do this proof. Okay, I'll do one of these two proofs. Let's do the first one, 2-column, and the second one, flowchart. Okay, so let's do a 2-column proof here. So we're given angle ABD is the same as YXZ, and we're given these pictures, okay? So I'm going to go ahead and I'm going to write, well, we're given that, gosh, I'm actually not going to start with this given because I'm not going to use it yet. I'm actually going to go ahead and say angle ABD and angle DBC are linear pair. Okay, and I'm also going to say the same thing about the other picture. So I'm going to say angle YXZ and angle WXZ, right? YX, yeah, are a linear pair. Okay, that's what I'm going to say. And how did I know that? Well, I knew that from looking at the picture. So that was given to me. That was given by the diagram. Okay. Number 2, I'm going to say those same angles are supplementary. So ABD and angle DBC are supplementary. Okay. And then I'm going to say I'm going to say angle YXZ and angle WXZ are supplementary. Now, what I can do now, I'm going to so that was linear pairs are supplementary. That's the book calls it the supplement theorem. I like just writing that linear pairs are supplementary. Okay. And now step 3 here, I'm going to go ahead and pull in that other given. The other given is that angle ABD and YXZ are the same. So angle ABD is the same as angle, I think it was YXZ. Let's double check those letters. YXZ, yes. And that was given to us, but I'm only pulling it now because I'm using it now. And now look at this. Look at this, okay? So I know that ABD and YXZ are the same. So ABD and YXZ are the same. And remember, we have an angle supplementary to this, and an angle supplementary is we have a theorem that states if two angles are supplementary to the same angle or congruent angles, then congruent, right? That was our theorem. So if two angles are supplementary to the same angle, they're congruent to one another, but it doesn't have to literally be the same angle. It's also worded that if two angles are supplementary congruent angles, then they're congruent to one another. So I can go ahead right now and say angle DBC is congruent to angle WXZ, and that's how we reuse the theorem, right? It wouldn't be hard to reprove this, right? We can just say, oh, well, then these add up to 180, and if they add up to 180, right, like this plus this equals 180, and this angle plus this angle equals 180, and then we go, oh, well, then they're equal to each other by transitive, so this angle plus this angle equals this angle plus this angle, and then we go, oh, the angles are the same, so we can subtract it from both sides and cancel out. We get the angles are the same. So it wouldn't be hard to reprove, but we don't need to add all those steps because we already did it. We just invoked that theorem, right, that if two angles are supplementary to the same or congruent angles, they're congruent to one another. Okay, I'm going to pause here. So I'm actually late getting back to Zoom. I got one more proof. I'll do it with a flow chart when we come back. All right, I'm back. Okay, so we're just going to do this last proof. I'm going to do flowchart proof because I love flowchart proof. So what we've got here is this whole angle is the same as this whole angle, but they share this part in the middle. And so we're just going to do some subtraction to get that this outer angle is the same as the other outer angle. So we're simply going to do some segment addition postulate and some subtraction. So good use of what we know so far. Very similar to what we did with segment addition postulate. Okay, so rather than starting with this given, because I'm going to use that in like a substitution transitive kind of way later on, I'm going to start instead with the segment addition or angle addition postulate. So I'm going to go ahead and write, well, the measure of, and I'm going to do this angle plus this angle first. So the measure of angle, and let's change this color in here. Let's get to blue. That's a little easier on the eyes for you. Let's go with purple. Okay, so we got the measure of RST plus the measure of angle TSW equals the total angle, which is the RSW, and that's where this is going to come in, right? And then we've got the same thing, but with two other angles. So I'm just going to move this to the side a little so we got enough room for the other. So I'm going to say the measure of angle WSU, the bottom one, plus that middle same angle we share, TSW, is equal to the measure of angle TSU. And how do we know those? Well, those are the angle addition postulate, right? You could also say and given by diagram, but it's really the angle addition postulate that is telling you those two angles add up. And now what we want to do is we want to link those together, okay? So what I'm going to do is I'm going to say, let's move this. I'm going to bring this in a second, okay? So I'm going to say now we will do the given. Let's do the measure of angle RSW is equal to the measure of angle TSU, and that was given. And so those two combine to give us, and again, I'm going to move this step down for when I need it, and I'm going to actually draw these arrows over a little further. That's the nice thing about a flowchart, right? You can kind of rearrange it, move it around. So these two combine to now say the measure of angle RST plus the measure of angle TSW is equal to, and I'm going to substitute this out or use transitive property, either one, and I'm going to now say it's equal to the measure of angle TSU. Okay? So again, you could use substitution or transitive. I'm going to go with transitive this time. Transitive property of equality. Okay? Well, now we've got two different things that add up to TSU, right? We've got this is TSU, and we've also got this is TSU, and I'm pulling this in now that I need it. Okay? It doesn't come from anywhere other than the diagram. So now I can say, though, these two together tell me that the measure of angle RST plus the measure of angle TSW is equal to the measure of angle WSU plus the measure of angle TSW, right? Because they're both the same as TSU. And now that I have that, and again, transitive or substitution, I'm going to go with the transitive property of equality because it's the most specific to this situation. And then I'm going to say, well, if they're both equal, well, they both have this extra, like, TSU added on both sides. So I could just go ahead and subtract that. And so what I end up getting is the measure of angle RST is the same as the measure of angle WSU. And that was the subtraction property of equality. Again, if you're on IXL or in, like, future chapters, we would probably just call the reason there algebra. But let's just double check. We wanted RST was the same as WSU, and that's exactly what we got, so we're done. All right, guys, I hope you enjoyed the video. Lots of practice just doing basic proofs with angles and develop some really useful ones, like the vertical angle theorem. All right. I actually wanted to, I changed my mind. I wanted to add in a little IXL practice at the end because they use some different vocabulary I want to make sure you're familiar with. So let's do some C8 or proofs involving angles here. So it starts out giving you most of the proof. So you want to prove that S and R are complementary and R and T are complementary. So prove that, so this is just proving that if two angles are complementary to the same angle, then they're congruent. And so it starts with complementary, uses the definition of complementary to get to math. Then it says let's set them equal. So that's either transitive property of equality or it's substitution. And then they go ahead and subtract the measure of angle R. So we would say that's a subtraction property of equality, but IXL says that's algebra. And then how did they get from the measures are equal to the angles are equal? Let's look. So that's the definition of congruent angles. There we go. Or they call it just the definition of congruence. So let's submit. Okay. Then we're going to go ahead on the next one. See, complete the proof that these two angles are congruent. And it's telling us congruent angles. So they go straight to angles add up to 180 because angles forming a linear pair sum to 180. So that's a little different than how the book uses it or how I use it. But notice that they're first saying that TXU, so this angle right here, and I can even turn on my drawing on Chrome. So they're saying this angle right here is this adds up with this UXV. So they're saying adds with this angle to make 180. And then separately what they did is they said, okay, in UXV, so that's this angle right here plus this angle right here, add to 180. Okay, so both of those were linear pair. Got it. Okay, I'm going to go back to just using my mouse here. And so then it says, well, then they're equal to each other. Again, transitive or substitution. And then how did we get to here? Well, we subtracted the same thing from both sides. We subtracted this measure of angle UXV. So that right there is going to be subtraction property of equality, or they call it algebra. Okay, so I'm just going to hit the Enter key, and it goes to the next one. I want to clear sorry, erase all, there we go, my drawings. Okay, so given two pairs of perpendicular lines, we want to complete a proof that these are the same. Okay, so perpendicular was given. Okay, so perpendicular lines, the very definition of perpendicular lines, depending on your book or the place, is either that they form right angles or that they form 90-degree angles. I'm okay with you using either one. But the definition of perpendicular lines, okay, is the measure is equal to 90, and then the measure of the other one's equal to 90. Well, then the two measures are the same because they're both 90, so that would be transitive, or that would be substitution because we're in equality. And then we're saying, okay, well, that means they're congruent. That's the definition of congruent. So up here, how did we get that 90-degree angle? Well, we use this step 2, and we just use the definition of perpendicular lines. I'm going to submit that. Okay, so we made it to tier 2. So now they're asking multiple choices and we have more possibilities. Oh, only 5 there, but it starts to get more and more possibilities. Okay, so we start with supplementary. How did we get that they add up to 180? That's the very definition of supplementary angles. Okay, and this last one, they got some algebra to get the measure of h is the same as the measure of g. So we go ahead and say then the angles are congruent by the very definition of congruence. Okay, so let's submit that. All right, so we're already at that SMART score of 60, which sometimes we're aiming for, sometimes we're aiming for a lot higher. But you can see now we're starting to develop more and more proofs ourselves. So we're given that the lines are perpendicular. Okay, so, oh no, sorry, that's what we're trying to prove. We're given that these two angles are congruent. Okay, and we know that angles form linear angles, or linear pair, sum to 180. So we can say these two angles add up to 180. We can also say another linear pair adds up because angles forming a linear pair are, oh no, that's not it. Let's actually draw on it. That was my mistake going to assumption. So TXU, so that's this one, plus UXV, that's this one, add to 180. That's angles forming a linear pair. So then how did they replace UXV with TXU? Well, that was because they were the same. So right there, what we did was use substitution. So I'm going to go over here, and that's the substitution property of equality. And then what did they do to get here? Well, what they did is they combined these two terms to get 2 of those equals 180, and then they divided by 2. So the combining like terms and dividing by 2, they lump those 2 steps together as just algebra. Okay, and once you have the 2 lines form a 90-degree angle, that means they're perpendicular. And again, the way you get to or from a vocabulary word like perpendicular, and I know it's a symbol there, but it's a spoken word, it's a definition that we need to know. The way you get there is by the definition of perpendicular lines, okay? All right, so let's do another one. I'm going to clear that palette there. So we have 2 pairs of complementary angles. So we get that those same 2 pairs add up to 90 because that's the very definition of complementary angles. Then we're going to go ahead and say, well, then the 2 pairs of angles sum up to the same thing, so they're equal to each other, the 2 sums, and that's by either substitution or transitive property of equality. Both will get marked correct. I'm going to choose transitive just because that seems to fit better here. It's more specific. Then we use algebra. Specifically, we're subtracting the measure of angle, f on both sides, to get these 2 angles' measures are equal. And then that means that the 2 angles are congruent by the very definition of congruence. Okay, so how do we get that these 2 angles add up to 180? EIF, that's this angle, and GIH, oh no, I read a little bit of line 1, a little bit of line 2, and FIG. So these 2 angles add to 180, and that's angles forming a linear pair, sum to 180. Then we have FIG, this one, and GIH, this one. So these 2 angles add to 180. That's the same reason. And then we get that they're the same. That's a transitive property of congruence. You're starting to see most of these, or of equality, this is algebra. You're starting to see that a lot of these start to look the same, right? Because we don't have that many tools yet, so the proofs do end up looking the same. As we learn more and more tools, they start to become different. Okay, let's look. Angle EIF is the same as GIH, so we just subtracted a fig here. And so that's algebra, or subtraction property of equality, and then definition of congruence to get here. I'll just do 1 or 2 more because you can tell they're starting to get the same. But we're doing every single reason in the proof here. Okay, so we were given that they were perpendicular. We were also given, and we can type here. We were given that it was perpendicular, and then here we know they're 90 because that's the definition of perpendicular lines. And then same thing here. We are given that's the definition of perpendicular lines. Well, then they're equal to each other. That's the transitive property of equality, is not congruent symbol. And then we know they're the same because that's the definition of congruence, okay? All right, now we have to actually type some symbols here. So it's asking complete the proof that these are congruent. So we need to pick that we have angle U is congruent to angle T. And the reason here is the definition of congruence, okay? And we could add lines down below if we want. Okay, oh, look at this. The challenge zone. Enter, enter, enter the challenge zone. Okay, so we got this is equal to 180. This is, oh, they substitution, right? So is that proof we already did? So they substituted out this value here. They substitute out this value and they put this in its place. Then we use algebra to say 2 the same thing. Adding to 180 means it's 90. And so then we can say, again, we're trying to complete the proof that these two lines are perpendicular. So if they meet to form a 90-degree angle, well, then I can say that line Vx, I always know the last step of the proof has to end with the exact way they want it, is line UW. And the way we know is the definition of perpendicular lines, okay? And then as we get closer and closer, we might have to add steps. Again, this one's not. It's just saying angle K. All right, I think this will be the last one, but eventually it asks you to create the entire proof yourself, and that is great practice, okay? Whoops, I did a less than symbol. J, and this would be the definition of congruence. All right, you guys, hope you enjoyed the video.